this video, we want to look at the hanging mass on a spring problem and solve for the length of how much the spring is stretched when we hang a mass on it. So we can use forces to figure this out. We could also use conservation of energy, but in this problem, we're going to focus on the force. So our problem says that we have a mass of 5.82 kilograms hung from a spring with a spring constant of 500 newtons per meter. How much is the spring stretched when it is in the equilibrium position? And we want to know what the original length of the spring is without the mass if the total length is 48.2 centimeters. So let's draw a picture here and write down what we know. So we have a spring here unstretched without the mass on it, and then we hang a mass on it. And it stretches a distance we're going to refer to as delta x. So it's just a change in the length. And here is our mass. We know that it is 5.82 kilograms. And we know that K, the spring constant, is 500 newtons per meter. So we'll go ahead and we'll call this unstretched length L1, and we'll call this total stretched length L2. And according to the last part of this problem, it says that L2, the total length, is 48.2 centimeters. The total length with the mass on it. So in the first part, we just want to find delta x, so how much the spring has stretched, the difference in the length. So we can use Newton's second law, so that's going to be the sum of the forces, also called the net force, is equal to the mass times the acceleration. Now, we're solving this problem at equilibrium. When a spring is at equilibrium, the mass here isn't moving, the spring isn't moving, so the acceleration is 0 meters per second squared. So the sum of our forces equals 0, and the sum of our forces are going to be the spring force in the positive direction minus the weight of the mass. So these are equal to 0. So our two forces acting here, the forces that are acting on the mass are going to be the weight of the mass, and then the spring force pulling it up. And when it's in equilibrium, these two forces have to be balanced, right? So we can move the weight over to the other side. We get F equals the weight. Now, the spring force itself is equal to K times delta x. And the weight of the mass is just going to be mg, right? So now we have an equation with delta x in it. So let's just solve for delta x by dividing both sides by k. So we have mg over k is equal to the distance that the spring has been stretched. So let's just go ahead and plug in the values that we have. So that's 5.82 kilograms times g, which is just 9.81 meters per second squared, and our spring constant, 500 newtons per meter. So this is going to give us a length of 0.114 meters. And if we want to go ahead and put this into centimeters, since we know that the total length is 48.2 centimeters, we could say that this is also equal to 11.4 centimeters. So let's figure out what the original length of the spring was without the mass. So just looking at these two different lengths here, we can see that L2 is going to equal delta x plus L1, right? So L2 is just this total stretched length. And then that's just equal to L1 plus delta x. So we just want to find L1, so let's subtract delta x from both sides. And that's going to give us L1 is equal to L2 minus delta x. And so that's 48.2 centimeters minus 11.4 centimeters. And that is just going to give us 36.8 centimeters. Or if you want to convert this to meters, we can move the decimal point over to get 0.368 meters. And that's how you would go about this kind of problem. In another problem, we'll use the conservation of energy. So hopefully this was helpful, and let me know if there's anything else that you'd like to see.